Hello, dear friends. Good morning to all of you. Once again, I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Dear friends, in applied electronics and instrumentation, we have seen almost all the articles except one or two articles. In last video, we have gone through the digital electronics, the basics of the digital electronics and logic gates which are used in the digital electronics. Now, as per your syllabus, after learning this basics of digital electronics, we have the Boolean algebra and then theorems related with this algebra. That is De Morgan's theorem. So we will go for the Boolean algebra today. Let us see this Boolean algebra. What is this Boolean algebra? In 1854, logical algebra was published by George Boole, known today as Boolean algebra. It is convenient way and systematic way of expressing and analyzing the operation of logic circuits. And in 1938, Claude Shannon was the first to apply Boole's work to the analysis and design of logic circuit, and from that it comes as Boolean algebra. Boolean operations and expressions. These are the some terminologies used in the Boolean algebra. Variable, a symbol used to represent a logical quantity. Complement, the inverse of variable and is indicated by a bar over the variable, like 1 bar. 1 bar means 0 and 0 bar means 1. That is complement. Literal, a variable or the complement of a variable is called as a literal, x or x bar. Boolean addition. Boolean addition is equivalent to the OR operation which we have already seen, OR gates. And through the OR gate we can perform the Boolean addition. This is called as logical addition. Like this, roughly I can read it, 0 plus 0 is 0. That means 0 OR with 0 is 0. 0 plus 1, that means 0 is ORing with 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1. This is called as logical or Boolean addition. It is called as OR operation. And these are the OR gates. 2 input OR gate. A sum term is produced by an OR operation with no AND operations involved. Like this, A plus B, then A plus B bar, then A plus B, then A bar plus B bar plus C bar, then A bar plus B bar plus C bar, C plus D bar, etc. These are the examples of the Boolean additions. And this is called as a sum term. A plus B here sum term. A plus B bar is the sum term, like this. A sum term is equal to 1 when one or more of the literals in the term are 1. Try to understand, a sum term is 1 when one or more of the literals in the term are 1. A sum term is equal to 0 only if each of the literal is 0. Here both the literal is 0, then sum term is 0. If one of the literal is 1, then the sum term is equal to 1. This is the theorem of the addition, Boolean addition, or expression or rules you can say for the Boolean addition using OR gate. Then Boolean multiplication. Boolean multiplication is equivalent to the AND operation. We have seen the AND gate. 0.0, that means 0 ending with 0 is equal to 0. 0 ending with 1 is equal to 0. 1 ending with 0 is equal to 0. 1 ending with 1 is equal to 1. This is called as Boolean multiplication. So a product term is produced by an AND operation with no OR operations involved. That is A dot B or AB bar, ABC bar, A bar, B, C, D bar. This is called as multiplication, Boolean multiplication. A product term is equal to 1 only if each of the literal in the term is 1. This is called as literals. Here A and B are the literals. A, B bar is the literal. A, B, C bar is the literal. A bar, B, C, D bar, these are individual literals. And if each literal is equal to 1, then product term is 1. That means each literal having a value 1, like this. This A is 1 and B bar is 1. Then the product is 1. A product term is equal to 0 when one or more of the literals are 0. Any one of the literal is 0, then product term is 0. This is called as Boolean multiplication using AND gate. Now laws and rules of Boolean algebra. The basic laws of Boolean algebra are the commutative laws, the associative laws, and the distributive laws. These three laws are used in Boolean algebra. Let us see these laws. First one is the commutative laws. The commutative law of addition for two variables is written as A plus B is equal to B plus A. You can interchange this. This is called as commutative law of addition. Here you can see this is OR gate, A and B. So this is addition is A plus B, or you can use here B or A. Addition is B plus A. So this is possible. You can change the literal from its places. It doesn't affect. This is commutative law. The commutative law of multiplication for two variables is written as A dot B is equal to B dot A. In the same way, like addition, this multiplication can also be done. Here you can see AND gate A, B. A is the input, B is the input, A dot B is the product. Or you can change B is the input, A is the input, B dot A is the product. This is dot here, not sum. So this is the commutative law for the multiplication. Then associative laws. The associative law of addition for three variables is written as A plus in bracket B plus C is equal to, in bracket you can write A plus B and then plus C. This is called as association, associative. And this can be implemented like this. Here two OR gates are used, A, and here another OR gate having the two inputs B and C. Then this is A plus B plus C is in bracket B plus C. Or you can equivalently write here this OR gate having inputs A and B and another OR gate having inputs C and this output. So this is A plus B into C. So this can be implemented, and this is called as associative law of addition. For three inputs are shown here. Similarly, you can have the number of inputs and you can associate each input and produce such type of outputs. Then the associative law of multiplication. Associative law of multiplication for three variables can be written as A into bracket B dot C, or is equal to A dot B in bracket and then C. This is called as associative law of multiplication. In similar way, you can use for AND operations. A is the input, B and C is another AND. You will get A and this is in bracket B and C. Or you can use this AB and this is C, and you will get here AB into C. Two AND gates are used. Here also two AND gates are used. So you can have to just change. It is a very simple. This is associative law of multiplication and associative law of addition for three variables. This is for addition. Additive is for this OR gate, and multiplication is using, addition is using for OR gate and multiplication is using for AND gate. Then third law is the distributive law. Commutative law is over. Associative law is over. Now this is distributive laws. The distributive law is written for three variables as follows. A into bracket B plus C. Here now AND and OR both operations are there in distributive law. So you can write here A dot B into plus A dot C. This is called as distribution. This bracket is removed and it is distributed AB AC like this. AB plus AC. So you can use the OR gate here B plus C. So B is the input and C is the input. You will get the B plus C. And another AND gate, this is ending here. You can use A here. So the A into B plus C you will get here. The same can be implemented. Here one OR gate and one AND gate is required to the left side. And to the right side we need two AND gates and one OR gate. A is the input, B is the input. Another AND gate is A is the input, C is the input. So here AB and here AC. So you will get here AB plus AC. So this implementation can be done by the law called as the distributive law. So distributive law is also important while minimizing the logical equations or logical circuits. Rules for Boolean algebra. These are the laws which we have seen: commutative law, associative law and distributive law. After this, these are the certain rules. You can go through this rule like this: A plus 0 is equal to A. This is just law of addition, ORing. A plus 1 is equal to 1. This is also law of OR principle of OR gate. Then A dot 0 is 0, A dot 1 is A. This is the principle of AND gate. A plus A is equal to A. This is the principle of OR gate. A plus A bar is equal to 1. 0 plus 0 bar. 0 bar is 1. So 0 plus 1 is 1. A dot A, that is 1 dot 1 is equal to 1. Principle of AND gate. A dot A bar is equal to 0. 1 dot 1 bar. 1 bar is 0. So A dot 0 is 0. Similarly, A bar A double bar is equal to A. Double bar means 2 times inversion. NOT gates are used. A bar means A followed by NOT gate and again followed by NOT gate. So it will be original. A double bar is equal to A. Then A plus AB is equal to A. Then A plus A bar B is equal to A plus B. Then in one bracket you write A plus B into in another bracket A plus C. This is ending up 2 brackets. A plus B multiplied with A plus C. Logical multiplication. Then you will get A plus B C. A plus B into C. That is A plus B ending with C. So these are the simple rules used in Boolean algebra for solving the different logical expressions. Then, along with this Boolean algebra, we use the De Morgan's theorem. This is also very important in digital electronics, which this is also in your syllabus. De Morgan's theorem provides mathematical verification of the equivalency of the NAND and negative OR gates and the equivalency of the NOR and negative AND gates. What the De Morgan's theorem provides? The equivalency of NAND and negative OR gates and the equivalency of the NOR and negative AND gates. Let us see De Morgan's theorem. The complement of 2 or more ANDed variable is equivalent to the OR of the complements of the individual variables. The complement of 2 or more ANDed variable like this, x AND with y has a complete complement, is equivalent to the OR of the complements of the individual variable. Then this is x bar plus y bar. X dot y whole bar is equal to x bar plus y bar. Individual complement with OR. Whole complement with AND. This is called as first law. De Morgan's theorem's first law. Then second law states the opposite of this one. The complement of the 2 or more ORed variables. You can see this x and y are the ORed here and having the complement to the AND of the complements of the individual variables is equivalent to the AND of the complements of the equivalent variable. Here x plus y whole bar is equal to x bar dot y bar. ANDing. This is ORing. Here ANDing and this is OR. So this is another law of De Morgan's theorem. So first De Morgan's theorem states that x dot y whole bar is equal to x bar plus y bar. And x plus y whole bar is equal to x bar dot y bar. So these are the De Morgan's theorem. So very important thing while solving the Boolean expressions, logical expressions, we must know the Boolean algebra and De Morgan's theorem. Right? So here the just one exercise. Apply the De Morgan's theorem to this expression. X dot y dot z whole bar. X plus y plus z whole bar. X bar plus y bar plus z bar whole bar. And then w bar dot x bar dot y bar dot z bar whole bar. You have to apply the De Morgan's theorem through all these 4. Then again another exercise. Apply the De Morgan's theorem to the expressions a plus b plus c whole bar, a plus b plus c in one bracket into d whole bar, abc plus def whole bar, ab bar plus c bar d plus ef whole bar. Again here a plus b c bar whole bar plus d into bracket e plus f bar bracket whole bar and whole bar. So this type of expressions can be simplified by using the De Morgan's theorem. So dear friends, students, the rules of the Boolean algebra and this 2 De Morgan's theorem are very important to solve this type of equations, this type of logical expressions. And by solving and minimizing these logical expressions, we can prepare the circuit that is minimum with a minimum requirements of the gates. Is called as optimized circuit. We can reduce into optimizing form. So Boolean algebra provides a concise way to express the operation of the logic circuit formed by a combination of logic gates, so that the output can be determined for various combinations of input values. Boolean expression for a logic circuit. To derive the Boolean expression for a given logic circuit, begin at the leftmost inputs and work toward the final output, writing expression for each gate. So from left to right you can say, go to solve by Boolean algebra and De Morgan's theorem, and you can get the output like this. This is the circuit showing for Boolean expression. Then constructing a truth table for a given logic circuit. So dear friend, today it is sufficient for today. Tomorrow we will go for the logic circuit and remaining two gates, XOR and XNOR gate. So that we will see tomorrow, and some logical circuit, solution of some logical circuit using Boolean algebra and De Morgan's theorem. So thank you very much for today's video. Observe it, go through it, and go through the details of the digital electronics. Thank you very much. If you have any difficulty, you can ask me at any time, please. Thanks a lot. Thank you very much.